Swayam Prabha. Digital India. Educated India.
Welcome friends to this last lecture of week 8 and we are talking about the soil pollutants. So in the last 4 lectures we have completed different inorganic pollutants of the soil and we started the organic pollutants of the soil. Among the organic pollutants we have discussed about the cationic organic pollutants and we started with the basic organic molecules. So, we will start with the basic organic molecules from today's lecture for today's lecture. So, several members of this as I have told in my last lecture that several members of S triazine family were selected as examples of these basic compounds. Okay. And the triazines are basically heterogeneous or heterocyclic nitrogenous nitrogen derivatives. You can see basically the heterocyclic nitrogen derivatives and the ring structure being composed of nitrogen as well as carbon atoms. Most triazines are basically symmetrical and the substituent as at the R1 position determines the ending of the common name. So, this is basically symmetrical triazine and this is example of asymmetrical triazine. So, another important point is with chlorine atom the common name ends is basically triazine and when the methyl thiol groups are present then the name ends with triene and when the methoxy groups are present OHC3 groups are present then that is the name of the compound ends with ton. So, the solubility of the compound is determined by the R1 substituent with the OCH3 substitution resulting in the highest solubility. So, when the R1 gets substituted by the OCH3 that is the methoxy group then it shows the highest solubility. The presence of electron rich nitrogen atom confers on on S triazine the well known electron donor ability that is weak basicity. So, this is about the basic organic molecules. If you consider the solubility of the basic organic molecules, remember the symmetrical triazines have low solubility in water and the 2-chloro S triazines being less soluble than the 2-methyl thio and 2-methoxy analogues. Water solubility increases at pH values between pH 5 and 3 due to strong protonation for 2-methoxy and 2-methyl thio S triazine and at pH 2 or lower for 2-chloro S triazine. So, again water solubility increases at pH between 5 to 3 due to strong protonation for this compound that is 2-methoxy and 2-methyl thio S triazine and at pH 2 or lower for 2-chloro S triazine. Structural modifications of the substituents significantly affect solubility at all pH levels. Structural modifications of the substituents significantly affect solubility at all pH levels. Now, basic organic molecules also show photodegradation. So, the S triazine and especially the chloro S triazine are partly photodecomposed in aqueous system by UV and IR radiation including sunlight and methoxy substituted groups are not photodegradable and most S triazines are relatively volatile. So, they can be lost from the aquatic and soil system by volatilization process. So, third one is acidic organic molecules. So, the acidic organic molecule this group of compound comprises various family of chemicals including substituted phenols, then chlorinated aliphatic acids, then chlorophenoxy alkanoic acids and substituted benzoic acids. Again 4 substituted phenols, then chlorinated aliphatic acids, then chlorophenoxyalkanoic acids and substituted benzoic acids. Now, substituted benzoic acid possesses carboxyl or phenolic functional groups capable of ionizing in aqueous media to yield anionic species. So, substituted benzoic acid produces anionic acids in aqueous media. Now, these materials range in acidic strength from strong acid. The strong acid example is trichloroacetic acid, in small v known as TCA, to relatively weak acids such as this 4,4-chloro O toluloxybutyric acids. In short, we call it MCPB. So, for example, the benzoic herbicides are derivatives of benzoic acids which contain chlorine atoms, methoxy or amino groups. Okay. So, this is an example of benzoic acid molecule. So, you can see benzoic herbicides are derivatives of benzoic acid. So, benzoic herbicides are basically derivative of this benzoic acid which contains the chlorinated atoms, methoxy and amino groups. In general, the benzoic herbicides are applied to both plants and soil. So, these are some of the examples of acidic organic molecules. So, another important example of this acidic organic molecule is dicamba and 2,3,6 TBA, common name is basically 2,3,6 dichlorobenzoic acid. These two are two benzoic herbicides with similar chemical structure. So, you can see this is an example, this is a chemical structure of dicamba which is basically 3,6-dichloro-2-methoxybenzoic acid. So, basically this is an important acidic organic molecule. Similarly, this 2,3,6 TBA or this 2,3,6 dichlorobenzoic acid is another important acidic molecule with a similar chemical structure. Now, in dicamba the chlorine atom and at the number 2 position is replaced by a methoxy group. So, here you can see that number 2 position the chlorine atom has been replaced by this methoxy group. Now, chlorinated aliphatic acids show the highest water solubility and the strongest acidity among the group of chemicals. So, it has a strong electronegative inductive effect of the chlorine atom which replace the hydrogen in the aliphatic chain of these acids. So, these are some of the examples of acidic organic molecules. Now, acid pesticide, what are the important acid pesticides herbicides like 2,4-D, 2,4,5-T, 2,4-D is basically short form of 2,4-dichlorophenoxyacetic acid. Okay, and 2,4,5-T is 2,4,5-dichlorophenoxyacetic acid. Then picloram and dinoseb. So, these are acid pesticides and they basically are characterized by their ability to ionize in aqueous solution forming anionic species. Now, at pH values lower than their dissociation constant which is denoted by pKa. So, at pH values which is lower than their dissociation constant, the molecular form will be present and increasing the pH above pKa will favor the dissociation. So, again pH value, when their pH value is less than their dissociation constant which is denoted by pKa, then the molecular form will prevail. However, when the increasing the pH above pKa will favor the dissociation. Now, both 2,4-D and 2,4,5-T are among the most widely known and used phenoxyalkanoic acid pesticides. Okay, so, in general the small organic molecules are characterized by this phenoxy basically have the following structural formula. So, basically they have a phenyl ring followed by an oxygen and then an aliphatic acid. So, as you can see here there is a phenyl ring followed by an oxygen and then oxygen basically acts as a link and then there is a aliphatic acid chain. So, this is the basically structure of this phenoxy of this phenoxy's structure. So, the phenyl ring is attached to an oxygen as you can see which is attached to an aliphatic acid, we know that. So, the length of the carbon chain of the aliphatic acid determines the name of the herbicides. Obviously, among the small acid molecules we may also mention different halogenated benzoic acid used as herbicides and chlorinated aliphatic acids used as basically insecticides. Okay. So, this is basically some of the important examples of acidic organic molecules. So, the fourth category is non-ionic organic molecules. So, the small organic molecules included in this group basically do not ionize significantly in aqueous systems and vary widely in their chemical composition and properties. And the groups which belong to this class are chlorinated hydrocarbons, organophosphate, carbamates, urea, anilines, anilides, amides, uracils and benzonitriles. So, these are the major groups of compound which are belong to this class. So, the great difference among the properties of these groups and even among compounds within a group are reflected in the variability of their adsorption behavior. Now, organic colloids are mainly responsible for the adsorption of these colloids, absorption of these chemicals. So, organic matter in the soil takes a major role for adsorption of these chemicals and controlling their mobility in the soils. Now, let us start with the chlorinated hydrocarbons. Widely known as these insecticides, widely known as insecticide group, basically they include DDT, then toxaphene, then linden, chlordane, aldrin, dieldrin. So, the major insecticides are basically basically denoted by these chlorinated hydrocarbons. Here you can see the structure of DDT, diphenyl trichloroethane. So, the compounds in this family basically in this chlorinated hydrocarbons exhibit long persistent, this is the major important point. It is basically all these organic molecules or pesticides shows long persistent in the soil. So, their use has been decreased dramatically during the past few years. So, since they can reside in the soil for long duration of time due to their high persistence, their degradation is very slow. As a result, their application in agriculture has been decreased dramatically by regulations and laws for the last couple of years. Now, with the exception of linden, all chlorinated hydrocarbons exhibit very low solubility in water. For example, DDT, toxaphene, then chlordane, aldrin, dieldrin, these are very less soluble in water. Now, DDT is about 10 times less soluble than other compounds of this family and is therefore considered to be immobile as a result as a solute in the soil system. So, as a result of that, DDT has been banned for agricultural operations. DDT is very less soluble and also very immobile in the soil. So, they can persist in the soil for a very long period of time. As a result of that, their application into the soil has been drastically controlled or reduced. So, the endrin, then dieldrin and and aldrin all show high water solubility and are therefore slightly mobile in soils. The vapor pressure of or chlorinated hydrocarbons varies basically very widely. If we consider low vapor pressure, it basically comprises DDT, endrin and dieldrin. Moderate vapor pressure you can see toxaphene and aldrin. High vapor pressure you can see chlordane and linden and very high heptachlor. So, volatilization of DDT from soil and other surfaces is therefore almost insignificant. So, as a result of that, DDT can persist in the soil for long period of time. So, DDT has low vapor pressure, as a result of that volatilization of DDT is low from soil surface and that is why DDT is highly persistent in the soil. Now, next comes the organophosphate pesticide. Now, organophosphate pesticides are basically part of the phosphoric acid ester group with a general formula of this. Now, you know the ester. Ester basically forms when acid reacts with the alcohol. So, basically this is you can see this is a phosphoric acid ester group where this R basically shows the alkyl group. Now, these esters are stable at neutral or acidic pH, but susceptible to hydrolysis in the presence of alkalis, where the POX ester bond is broken. So, the POX ester bond is broken due to the presence of alkaline condition. Now, the rate of this process is related to the nature of the constituent X. to the pressure of these catalytic reagents and then the pH of the and the temperature. So, all these factors, nature of the constituent X, then pH, temperature, pressure of catalytic agents, all these influence the degradation of or the hydrolysis of different organophosphate pesticides. Now, organophosphates are more toxic than chlorinated hydrocarbons, particularly to human, but they exhibit lower persistence in soils. Now, this behavior is also related to an enhanced water solubility and higher vapor pressure of organophosphates. So, basically these organophosphates are more toxic than chlorinated hydrocarbons, specifically as far as the human toxicity is concerned, but they are less persistent in the soil as compared to the chlorinated hydrocarbons. So, malathion and parathion, as you can see here, I have put the structure of malathion and parathion. So, malathion and parathion insecticides are known as known to be chemically hydrolyzed and biodegraded by microorganisms in soil systems. So, these are two important organophosphate pesticide. The most used organophosphate herbicide is basically glyphosate. Another group is phenyl carbamate and substituted ureas. So, they are basically these are non-ionic herbicides. You can see here substituting 3 of the hydrogen atoms of an urea and other chemical groups such as phenyl, methyl and methoxy groups. So, what is the formula of urea? Urea formula is this is the formula of urea. Okay. So, this formula of the urea, so you can see substituting 3 of the hydrogen atom of the urea. So, here 3 of the hydrogen atom of the urea have been substituted with other chemical groups such as it can be either phenyl or methyl and or methoxy group produce the effective herbicides. So, the chemical structure of the substituted urea is like this one. So, this is this is known as either phenyl carbamates or substituted urea if the substituting group is phenyl group. Now, most urea herbicides are non-selective and are usually applied to the soil. So, they are non-selective, so they can kill any herb or any weed that come in contact with that herbicide. So, they are absorbed by roots and translocated apoplastically to the upper part of the plant. Now, you know what is apoplastic movement. So, when the movement of compound occurs through the cell wall, then it is called apoplastic movement. As you can see, the movement of the compound is happening through the diffusion through the apoplastic pathway or through the cell wall, as opposed to the symplastic pathway where the movement occurs through the cytoplasm. So, they are absorbed by the roots. So, these phenyl carbamates or substituted ureas are basically absorbed by the roots and translocated apoplastically to the upper part of the plant. Diureon is widely used as a pre-emergence herbicide for control of a large number of weeds. However, monuron has a much greater solubility in water than diuron and was the first urea type herbicide which is produced. So, these are some of the examples of substituted ureas. Now, carbamate and thiocarbamate herbicide, if you consider the structure of carbamates and thiocarbamates is given here. So, this carbamate and thiocarbamate. Now, in the thiocarbamate, one of the oxygen atom is replaced by a sulfur atom. Since the word thio is there, so obviously there will be presence of sulfur. So, in the thiocarbamates, one of the oxygen atom is you can see here this oxygen atom is replaced by sulfur in the thiocarbamate and other substitution also can occur in the. So, this is one of the important organic non-ionic organic molecules. So, carbamate herbicide, if you consider carbamate herbicides, the carbamates are basically soil or foliar applied. So, among the soil applied carbamates, examples are profam and then chlorprofam, and then if we consider the foliar applied carbamates, examples are azulam, then fenmidifam. So, these are the also herbicides. So, they are basically characterized by high specific selectivity on particular crops. Now, Profam applied to the soil is readily translocated to the plants when absorbed by the roots, whereas Chloroprofam is more persistent in the soil than Profam itself. So, these are some of the example or carbamate herbicides. So, if we move ahead and see thiocarbamate herbicides, then thiocarbamate are usually applied to the soils. Their high volatility necessitates the quick incorporation into the soil or application via irrigation water, and thiocarbamate pesticide are typified by butylate, which is basically a soil incorporated compound translocated upward to shoots via apoplastic movement. Following the root uptake, we have discussed apoplastic movement. One example of this thiocarbamate herbicide is EPTC, which is the short form of ethyl dipropyl thiocarbamate. So, ethyl dipropyl thiocarbamate, or in the short form that is EPTC, is a volatile soil incorporated herbicide that is absorbed by seeds, roots and emerging shoots in contact with treated soils. So, again Vapam is a temporary soil fumigant able to control these germinating wheat seeds and perennial weeds, and is applied and incorporated into the soils. So, these are some of the examples of thiocarbamate herbicides. So, if we move ahead and see, so the next major group is hydrocarbons. Shuru korbo? So, the next major group is hydrocarbons. Now, hydrocarbons, in the hydrocarbons, organic solvents and petroleum products are an additional group of potential organic pollutants. Now, you know that in general these products exhibit a low solubility in water, and most of them are apolar in nature or non-polar in nature. So, that is why they are not soluble in water. And regarding their origin, the polar material content weight percentage basis in crude oil varies from 2.9 to 17.9%, and the solubility of petroleum hydrocarbon in water increases with the increase of hydrocarbon polarity. So, basically if the hydrocarbon polarity increases, their solubility increases. Okay. But most of them are by nature are non-polar or apolar. So, the hydrocarbon groups are themselves mixture of components of various carbon structures. What are those carbon structures? You can see here N paraffins ranging from C11 to C32, then isoparaffins comprising 1 ring to 6 ring cycloparaffins, aromatics benzene, toluene, C8 to C11 aromatics, etc. So, you can see these are the different different components which basically mix together to produce the hydrocarbon. Now, if we see the fractional distillation of distribution of crude oil, refined oil, we see that as the boiling point range increases, the fractional distillation process can produce different fractions of hydrocarbons. So, gasoline fractions, they can be we can get them at the lowest boiling point, followed by these kerosene and then heating oil, followed by these diesel fuels, light gas oil, then light lubes, and heavy gas oil, and finally residuum, which is basically separated at the highest boiling range. So, basically when the boiling range or boiling point increases in this direction, then these different different fractions of hydrocarbons separate out. So, obviously gasoline fraction shows straight run gasoline, they are highly volatile in nature, and in the middle distillates you can see kerosene, heating oil, light gas oil, diesel fuels, jet fuels, okay, which are separate out. And in the white cut gas wells, you can see light lubes and heavy lubes, which are showing higher boiling range, and in the highest boiling range you can see residual soils as well as residuum. So, this is showing the fractional distillation of crude and refined oils. So, similarly here also you can see how this fractional distillation basically occurs. So, vapor gasoline first separate out, and then gasoline vapors produces LPG, and then naphtha ultimately produce gasoline, then kerosene which produces jet fuel, diesel distillates produce diesel fuel, medium weight gas wells, and ultimately heavy gas well goes to the cracking units, and then alkylation units produces LPG gasolines and also produce jet fuels and diesel fuels, and residuum which is goes to the coker ultimately produces the industrial fuel, and finally you can get the asphalt bases. So, this is how the different fractions of hydrocarbons are separated out from each other based on their based on their boiling point, and this is called the fractional distillation. Now, behavior of hydrocarbons, if you see the behavior of hydrocarbon, the petroleum product is not a homogeneous compound as we have just seen. It may be observed that the gasoline fraction is characterized by the lowest boiling point and produce the most volatile of the refined products. Oils with the highest boiling points are the least volatile petroleum fractions, and the evaporation rate of a specific hydrocarbon is a function of its vapor pressure, which is inversely related to the carbon number of the molecular weight. So, obviously compounds compounds with molecular weights greater than 15 will continue to evaporate over long period of time, although these rates become insignificant after 100 hours. So, more complex the structure of the hydrocarbon, more time it will take to evaporate. Another important compound is polycyclic aromatic hydrocarbon, or in short form that is called the PAH. So, PAH consists of 2 or more benzene rings arranged in various configurations with hydrophobicity increasing with molecular weight. So, you can see here I have produced different PAH here, starting from anthracene, phenanthrene, phenylene, tetracene and so on so forth. So, these are all the PAH compounds. They can be found as industrial effluents or arising from different anthropogenic sources, and they are characterized by a long half life and are basically hazardous at low concentration. They have got long half life and they are very hazardous at low concentration. Okay. So, they are very important potential pollutant as far as the soil and environment are concerned. So, another group of compound is phthalates. So, phthalates are another potential pollutants. Most of the industrially produced orthophthalic anhydrides is esterified with various alcohol to produce the phthalic acid diesters. Okay. In short form we know the phthalic acid diesters is known as PAE. So, which are used mainly as plasticizers. So, PAE are also used as pesticide carriers and insect repellents in dyes, cosmetic, lubricants. So, they are very lipophilic and and then lyophobic liquids of medium viscosity and low vapor pressure. So, they can produce a huge amount of environmental pollution if they exist in high concentration in the soil. DHP or di2 ethyl phthalate is a moderately viscous liquid and practically immiscible with water and has a very low vapor pressure, but it has been detected in various aqueous solutions together with other PAEs, and these chemicals are mostly regarded as pollutants from industrial sources. Their levels in the environment are high enough to threaten human health directly or indirectly through disturbance of the ecological balance. Now, if you consider the organic macromolecules, in the organic macromolecules there are of two origins. One is naturally occurring macromolecules and the second one is synthetic organic macromolecules. So, in the naturally organic macromolecules include basically humic acid and fulvic substances and positively and negative charge polysaccharides. So, the naturally occurring macromolecules could not be listed as soil pollutants, but they can play an important role in the soil pollution process as ligands of various inorganic and organic toxic chemicals. We have seen that these organic matter which is present in the soil produce chelates through the ligands by complexing these inorganic pollutants and sometimes organic toxic chemicals. So, that is why these naturally organic macromolecules could play an important role in the soil pollution. A polymer is characterized by a flexible chain of segments which affects its adsorption on soil solid phase. So, it could reach, that is the if we discuss, we have discussed the naturally occurring macromolecules. Now if we consider the synthetic occurring organic macromolecules, it could reach a land surface and as compounds used in soil hydro physical property reclamation or as pollutants following the human activities. Among the soil reclamation products, the following may be included. So what are these? Polyvinyl alcohol, polyacrylamide, then polyethylene glycol or polyethylene oxides, and polyvinyl pyrrolidine. All these polymers are water soluble and non-ionic, and their chemical structures are shown in the next slide. So you can see their chemical structure. So this is a polyvinyl alcohol, this is polyacrylamide, this is polyethylene glycol, and this polyvinyl pyrrolidine. So these are different non-ionic polymers. So these products are in general not toxic, but they can become a hazard by accidental disposal in high concentration on the land surface. So the phenols could be polymerized by mineral surface reactions or phenol with clays, leading to the formation of colored products, which in general are of high molecular weight of the parent compounds. So these are some phenolic compounds identified in methanol extracts of clear organic complexes, like this 2,6 dimethyl phenol, then 4,4-bis 2,6 dimethyl phenol, then quinone dimer, and also 2,6 dimethyl phenol trimer. So these are phenolic compounds which are identified in methanol extract of clear organic complexes. Also, another major important synthetic organic macromolecule is surfactants. So these surfactants are an additional group of organic molecules which reach the soil surface mainly as a result of sludge or effluent disposal. Now in the last 20 years, the biodegradable detergent has replaced the persistent one, and anionic surfactants such as these alkyl aryl sulfonate LAS have become the most popular detergents. Now this surfactant has a hydrophilic head. So this is basically a hydrophilic head which is remaining in contact with the water, and it has also a it has also a hydrophobic tail. So this hydrophobic tail basically goes to the oil or organic liquid. So it has hydrophilic head, as you can see here, this has hydrophilic head, and also this hydrophilic head remains in direct contact with aqueous solution, whereas this hydrophobic end goes directly in contact with the oil or organic solvent. So this is a structure of the surfactant. So the structure of this compound consists of a straight chain alkyl group, benzene or sulfonate groups. Now these surfactants are known as one of the major potential source of pollutant in soil. For example, is DDBS, that is dodecyl benzene sulfuric acid, and LAS, that is linear alkyl sulfonate. These surfactant contain relatively bulky substituent groups, where NaLS, that is sodium lacqueryl sulfate, has a filiform geometrical structure. Now what is the problem with these surfactants? Now prolonged exposure to surfactants can irritate and damage the skin, because surfactants disrupt the lipid membrane that protects the skin and other cells. Now skin irritancy generally increase in the series of non-ionic and amphoteric, anionic, cationic surfactants. So basically prolonged exposure to the surfactants can irritate and damage our skin, and also since they can disrupt the lipid membrane that protects the skin and other cells, and these irritations. So basically these surfactants are known as one of the major source of pollutants in the soil. So guys, we have covered a wide range of elements as well as organic compounds which are known as potential soil pollutants, which shows very important influence on soil pollution. I hope that you have learned something new in this chapter, and obviously if we go to the last slide, it is the references. This last slide shows the book which I have used for this chapter. This is basically Soil Pollution, process and dynamics. So, you can consult this book to get more information about different soil pollution process and dynamics. So, I would request you to go through and read this book in details to enrich yourself among the soil pollution. Although the time is limited, it is not possible for us to complete all these aspects of soil pollution pollutants. However, I have tried to cover the major pollutants which are known for their impacts as far as the soil pollution is concerned. I hope you have learned something new in this module, and let us wrap up this module and let us discuss other aspects of soil pollution in the next module, that is in module 9. Thank you very much.